to 4 minutes if there are any.
Okay.
Hey everyone, we have Preston Van Loon here. He's the founder of Prysmatic Labs, which is working on Ethereum 2.0, and I'll let him take it from here.
Hey guys, thanks for having me here. First of all, really excited. I love talking about this stuff. And it's especially exciting as we're so very close to the first phase of the multi-phase rollout for Ethereum 2.0. So what we're going to talk about today, we're going to just talk about everything from the beginning of Ethereum 2.0 and go to sort of the high level of what's to come and dive into some details there. So let's go ahead and get started. First of all, introducing myself and the team. We are Prysmatic Labs. We're a team of independent contributors, blockchain enthusiasts and experts have come together to help scale Ethereum. We work really close with a lot of other teams very similar to us. We work closely with the Ethereum Foundation, with the research team on building out Ethereum into the new model of proof of stake and sharding. Over the last 2.5 years, almost 3 years now, we've grown from just a few people to 9 people, and we have over 100 open source contributors. So it's really been a crazy ride so far, and it's just the beginning. Let's start with the basic. I'm sure you are all familiar with what Ethereum is, but for those that aren't, let's go ahead and dive into it a little bit. First of all, Ethereum is, I think, a little bit different than other blockchains, as we like to be a little more quirky and have a little more fun with things like this Doge and then the nine cat and all these kind of things. So it's definitely very interesting blockchain, but how does it work? Well, it's first of all, it's the goal is to be a decentralized world computer. So what this means is we have a open source blockchain, so anyone can view the code, they can see how it works. It builds this decentralized application platform where it's really distributed all across the world as one big kind of unstoppable computer. It has more redundancy than any of your normal centralized systems. So there's somewhere in the order of tens of thousands of nodes participating, and by nodes I mean anybody who's on the network that is syncing the chain or reading the chain or really operating it in any way. And we have lots of use cases with this kind of platform. We can build decentralized autonomous organizations or DAOs. You can launch your own token, and you can build these decentralized applications that are difficult or impossible to do using centralized models. Big picture, it's very detailed and complicated on how this system works. We're not going to go into all of it. I really just want to focus on just one piece of the Ethereum as it is today, and that is the proof of work mechanism. So how we come to consensus on the chain and how blocks are produced and all this kind of stuff. Using proof of work, it's basically a complicated cryptographic puzzle where you have the inputs in with some random number, and if that meets some partial hash collision, then we've solved the puzzle. We found the new block, and we can build on top of that. One of the big problems with that is it's very energy inefficient. So with Ethereum 2.0, we're considering how can we make this better, maybe through proof of stake. So it's important to take a look at proof of work. It's not to say the rest of this is not important. A lot of this kind of ideas and models and objects carry over in ETH2, but we're not really going to go into it in too detail. One thing I want to look at here is just kind of how a block is created, or what is a block made of. It has a reference to the previous block. It has all of the receipts and transactions and this the new state, resulting state, and some additional metadata. So looking at that, what does it really mean to scale Ethereum? What are we talking about when we say, oh, Ethereum doesn't scale very well, or how can we make it scale better? Let's take a look at three popular options for sending payments. So the first one here, we have Bitcoin. And on Bitcoin, your throughput, your maximum throughput is around 7 transactions per second, which on a global scale is not that great. And Ethereum is not that much better with a theoretical maximum of 27 transactions per second. It kind of depends on what the gas limit is for blocks, but if you were only sending balance transfers, not really interacting with contracts, then you could reach 27 transactions per second. But when you look at something like Visa, which is really powering most of the world's payments on a day-to-day basis, they have the capacity of going to 24,000 transactions per second, which is just, we have a long way to go if Ethereum or even Bitcoin aims to displace a technology like Visa. So it's really important to think about that. But in reality, the theoretical maximum numbers are not really getting hit. It's typically on the order of 3 transactions per second for Bitcoin, 12 for Ethereum, and then we think, based on an older report from Visa, it's something like 1,600 transactions per second. Block times are another important factor. So not only can we create a transaction, it needs to be included in a block. So that's sort of the minimum amount of time you can wait for a transaction to be included on the blockchain. So in Bitcoin, it takes 10 minutes to produce a block on average. On Ethereum, it aims to be 14 seconds. And for Visa, they don't have blocks. It's not really much of a factor. But if you think about when you go to the store and you swipe your card, how long does that take? It's on the order of 3 to 5 seconds. So again, if we aim to displace this type of technology, it's not really acceptable for the end user to have initiated a transaction and then be waiting into the double-digit seconds or even 10 minutes. It's just not going to work. So that's one of the things we would like to improve. We're talking about how do transactions fit into blocks, which is kind of what I was just saying. They are packaged in whatever order the block producer aims to choose, but typically they want to maximize their profits. So they want to choose the transactions that pay the highest fee, and because they get to collect those fees in the end. But one of the cool things about Ethereum is that the gas limit of blocks is dynamic, so it fluctuates a little bit. It used to be 8 million. I don't know what it is now. Maybe it's 10 million Gwei, but the algorithm there is that the limit is at least 4.7 million, and it changes over the last, like the moving average over the last 1,024 blocks or so. And for each block that proposes a change in either direction, it can only be moved by a small percentage, that being 1 in 1,024. Taking a look at the gas limit over time, you can kind of see that it moves a little bit, and then there's these big cliffs, which are actually typically over a day or two of miners or the community kind of agreeing on, all right, let's bump up the gas limit. So you can only move a little bit per block, but if everyone's working on it, then you have these big cliffs. So it is dynamic. It's not a fixed number. But taking all that in mind, we know how transactions fit into blocks, and we know that blocks come every interval. So what are some techniques we can do to go fast? How do we go faster and scale? Well, we want to make sure that we not only increase the scalability of our platform, but we do so without taking away from the decentralization aspect of it or the security aspect of it. So let's dive into a couple ideas on how we can scale and maybe why those aren't such great ideas. So one thing to consider is, all right, well, if gas limit is 8 million blocks or 8 million gwei, why don't we just change it to 80 million gwei? I mean, that's an easy 10 times improvement, right? Well, for bigger blocks, it means that you need more computing power to process those blocks. So that means that you need more resources just to be a participant. So you're kind of ruling out a lot of the cheaper technology, which means that it's less central, or it's more centralized in the sense that you've kind of made it impossible for some users who may not have access to more expensive hardware. Now they can't be a participant like they were before. They can't keep up with it. So that's a cool idea in theory, but yeah, it doesn't totally satisfy that trilemma that we were looking at. Another thing we can do is we can make blocks come faster. So in Ethereum, they were 14 seconds, but what if they were just 2 seconds? I mean, that's a 7 times improvement. Or what if it was only 1 second? That's 14 times improvement. Well, having more blocks coming around more frequently means that there's a chance that we have blocks being produced at the same time, or maybe that block didn't have enough time to get through the whole network. So you have a lot of forking going on. You have different paths on the blockchain that are being produced, and it makes it a little chaotic and kind of harder for the chain to remain stable, which means an unstable blockchain is more vulnerable to an attack, and that diminishes the security of the blockchain, right? The whole thing is that we can secure it and that it's stored in there forever, and that it's sort of like in a final state that we can trust. So that's a cool idea in theory, just reduce the time between blocks, but it's not going to be great. This trilemma has been, the biggest thing that we're thinking about. We want to increase scalability without giving up any of the other two aspects of the blockchain. So with scaling, there are essentially two types of scaling. Layer one is on-chain at the protocol layer. So imagine we're able to without having too much refactoring or reorganizing of things, we can just make the protocol itself a little bit faster. This is more difficult to do because you're talking about taking an existing blockchain and rewriting it in a way that changes the parameters of the protocol, but in the end makes it faster. And this, if done correctly, can satisfy the trilemma where we do get scalability without giving up the decentralization aspect of it or the security aspect of it. And it also benefits layer two. So what is layer two? It's anything really that's not on layer one. So if we can take some of the transactions we want to do and then do them somewhere else, and then maybe commit the result to the protocol layer or the base layer, that way you're getting a lot more throughput without having to leveraging the security of the core protocol, the base layer, but ultimately you're getting a lot higher throughput. This is easier to implement because you can do it in parallel to the protocol. You don't necessarily have to modify the existing protocol, especially on a blockchain that's already launched. That by comparison makes it a lot easier. And you have a lot more flexibility with this. Anyone can create their own layer two off-chain protocol and implement it and fit their needs exactly. It doesn't have to be like a canned application that you use. It can be more suitable for your needs. But with that, there is usually some trust assumptions or security assumptions with that. So it's not as secure as or decentralized as just doing things on the base layer. But for a lot of use cases, it makes a big difference in terms of scalability. So talking about the protocol upgrades and on-chain layer 1 scaling, here comes Ethereum 2.0. So we're kind of rewriting this protocol and trying to make it faster and change a bunch of different things. From the words of Vitalik, the creator of Ethereum, he's described Ethereum 2.0 as a big multi-year long upgrade that's going to massively increase the blockchain scalability through sharding, increase security with proof of stake, and just improve a bunch of things on the programmatic layer that necessarily, looking back in hindsight, we could have done a bit better. So needless to say, this is a large undertaking, especially when you have such a popular blockchain that's already running. It's pretty tricky and takes very careful research and planning and thinking about how to do this effectively. So let's go ahead and dive into it. The Ethereum 2.0 kind of development process, or maybe rather the rollout process, is we're going to do this in multiple phases. So instead of launching it all at once, we're going to start with phase 0 and being programmers or developers or software engineers, whatever you want to call it. We start counting at 0 instead of counting at 1. So naturally for us, it is phase 0, which is namely called the beacon chain. And this represents really the center of the universe of ETH2. So it's kind of like a guiding light in the system. It does a lot, essentially. So looking at these 4 important components of the beacon chain and what it's responsible for. First of all, it's responsible for maintaining the validator registry. So who's an eligible participant in this proof of stake blockchain, who's sent their deposit through, who's sent everything in, and then whether or not they want to exit or withdraw, and handling, balances and stuff. So we get the beacon chain is responsible for calculating all the rewards and penalties, which happen every epoch. It handles slashing, and then you have, either a liveness penalty. So if you're not participating, you get penalized. But if you are participating, you get rewarded. So it's incentivized in that way. The beacon chain is also responsible for our source of entropy. So we're currently using the Randall model, which is like a commit and reveal scheme. With this, we can effectively shuffle the validators so that it's extremely difficult to have a coordinated attack, because no one really knows what's the next set of validators chosen to agree on a certain piece of information, or the next validator that is selected to produce a block. We won't know this until a few minutes before that event is scheduled to happen. And then the final piece of the beacon chain, or rather, I think the most important piece, is with proof of stake, we can actually come to consensus on a piece of information that becomes final. Part of a problem with proof of work is that you can have what's called a 51% attack, where a piece of the blockchain becomes orphaned and effectively rewritten. It gets harder as time goes on, but it's not considered truly final. It's just kind of probabilistically final, or where it would be unrealistic to revert that information. But with proof of stake, it is final and not possible to rewrite that information. And that happens, when the chain's moving smoothly. It's happening every 3 epochs or so. This is a 3 epoch delay. So every 18 minutes, you will know that your transaction has been not only committed to the blockchain, but it is finalized, irreversible, and impossible to remove. So that's a really great piece, security piece there. So talking about proof of stake, we're using a design called Casper, the friendly finality gadget, where We have validators that have ETH at stake. This mechanism, instead of using, like proof of work, this computationally difficult puzzle, which requires, warehouses of computers or machines to do that. This is a simple, lightweight hardware that anyone can run, and it's really just signing a message. So it's orders of magnitude much more efficient on energy, and the requirements to be a block producer, by comparison, are much lower. Most people don't have access to a data center full of machines or a warehouse full of machines, but they might have a laptop that's 5 years old they don't use anymore, or maybe they can go buy a Raspberry Pi or something for under $100 and get set up and be a participant on the blockchain. That's great for decentralization. It means the barrier is lower, more types of people can join. And so let's talk about how might you become a validator. And by the way, this is available, multiple testnets going on right now. So if this is interesting to you, look up the ETH2 testnets and try this process out for yourself. But essentially, you send a 32 ETH deposit. So you send a message with some metadata and a 32 ETH value. This is included in the ETH1 blockchain. So there's a contract on the ETH1 blockchain. All of the ETH2 nodes are watching and observing the ETH1 blockchain, then voting on the state of that. So they're all coming to consensus on what is the new set or the new highest deposit in the deposit contract. And once those have been agreed upon, then they're included in the state of ETH2. It's okay, we've received all these new deposits. And for new validators, you go into the activation queue. So we have a rate limiter on ETH2 so that people aren't, surging, entering and exiting. It's a rate limiter of 4 validators per epoch. Epoch is 6.4 minutes. So going through this whole process, the minimum amount of time you're going to wait is just over 2 hours. So it is a little bit of a long process, but that is because it needs to be enough time for consensus and for the probabilistic finality of ETH1. So what does the validator do exactly? Well, you have two major roles. You're either you might be a block producer, and imagine that there are 100,000 validators in the system and only so many blocks produced per day or per week or per month. So you're very infrequently going to be a proposer, a block producer, but that's rewarded slightly higher. So that's kind of nice. What you are going to do every epoch is you're going to be in a tester, and you're going to attest to your view or the application's view of the state of ETH2. And then going into future phases of phase 1 and beyond. This is also cross-linking data between shards. And some terminology here. A committee is just a subset of validators. So acting as a block producer, what are we going to do when it's our turn to produce a block? Well, we assemble a block, kind of like what we saw with ETH1. It has a lot of information in it. We have the slot number, which is kind of like the block number. We have a reference to the previous block, a reference to the new state. We have a signature over the whole thing, and then we have some metadata, so including block operations and stuff like the slashings, exits, transfers, deposits, and attestations, and then your ETH1 data vote as a proposer. So you assemble all this, do the state transition, sign the block, and then blast it off into the network. Then it goes through the state. The state does some verification, processes the votes, and then processes all the objects, and then you get a new state out the other side. So attesting is very similar. You sort of look at what is using the Casper FFG algorithm. You decide, okay, which branch of the blockchain has the most votes, essentially, and then you you can broadcast that as your attestation. Say, I think this is the head of the chain. That's what I think, and then that gets aggregated together later, and then packaged into blocks. So it's essentially, you're broadcasting, attesting to your state of the world at a given time. High level, looking at the rewards and penalties. Like I said, proposing a block has a higher yield because it's less frequent. Rewards and penalties are calculated every epoch. And there's a key mechanism here that when we haven't reached finality, because we haven't been able to get 2/3 majority agreeing on the same thing, we're not getting finality. And when that has not happened for more than 4 epochs, the penalties start to increase severely, where that if after 2 weeks or so, participants that weren't participating, or validators that weren't participating, start to lose so much of their balance that they're kicked out of the system. So that's important to realize that ETH2, when the system gets into a bad state, it tries to, at a protocol level, get back to normal as fast as possible. Okay, that's phase 0. Phase 0 being probably the biggest piece, I think, of the puzzle here. It's laying down the rails and the framework for everything else. So we've got phase 0, which has no transactions yet or really any data yet. Now we're introducing the data layer, the shard chains. So shard chains sort of revolve around the beacon chain. And if you look at this diagram on the right, it kind of gives a sense of all the beacon chains in the middle and all of these shards which operate, independently of each other, are all linked together by this one part of the system, the beacon chain. These things run in parallel. This slide, sorry, is a little bit old. It says 1,024 shards. That was changed last year to 64 shards, so that we can get faster cross-linking and get things going faster. And still, a 64 times increased data throughput is a significant improvement over the existing state of Ethereum. So that's going to be nice. And with that, we're expected to come on to consensus about a data on the order of 10 megabytes per second. So it's quite a bit of data for a system to come on to agree about. And some things you can do with this is you can put zero knowledge rollups on there. You can have really any kind of system that's a write once, read many type of application. So like a Twitter, you can write on Twitter and put it on there. You can do website hosting. This can be your general data layer for small pieces of data. It wouldn't be good for video hosting or anything like that, but maybe small stuff. So phase 1 is pretty small. Phase 2 is when we're bringing in the Ethereum virtual machine and actual state execution. So executing operations of smart contracts. The plan here is that we have this existing Ethereum virtual machine, and we want to replace it with an Ethereum flavor of WebAssembly, so-called eWASM. With the phase 2, you have asynchronous cross-shard transactions. You can migrate contracts from one shard to another. This is contract yanking. And then this is typically when people think that Ethereum 2.0 becomes most useful, or at least resembles the state it was today with Ethereum 1.0. And this has been in research and development for quite some time, and it's starting to go into development this year. And it goes in parallel to phase 0 and phase 1. So all these phases are kind of overlapping each other, but being run in parallel. So just to recap this, Ethereum brings proof of stake and blockchain sharding. It's literally a whole new blockchain. It's not just a network upgrade. It's something that will run in parallel to ETH1 for a little while, for a few months or years, as those things phases roll out, and then we're migrating over. something we learned along the way is that designing the specification is very difficult to do from a research perspective, but implementing it is equally as hard, or if not harder. And in phase one, we're really close to launching. Everything's coming together, but we could always use more tooling and data analysis. If you want to hear more about the roadmap on exactly how phase one specifically is going to go, be sure to tune in to Terrence's talk. He's also from Prysmatic Labs. He's going to be talking on Tuesday at 5:30, and he's going to go into much more detail on phase one. And that's me, Prysmatic Labs. My name is Preston Van Loon, and I think if we have a little bit of time for questions here. Let's see. I think I see a question here that says, point us in the direction of the Ethereum client so we can fire up a node to help support ETH2. Not really a question, but a great comment. So if you'd like to participate, you can go to, let's see, I think it's prylabs.net. And this is a basic entry point on how to get into ETH2 and how to get into a testnet. And watch, it's not going to load because we're on live cast here. But yeah, there it goes. Check it out. Wow, I think this is an old cache site. But join our Discord. Ping me on wherever you can find me. I'll help you get set up. And we'd love your support on E2 and our testnet. So thanks for that comment.
Cool. So if you want to share any links with me, Preston, after this conference, I can share it out as well. Because it's a good thing. So we're going to transition to our next talk now. This was really great. Thank you so much.
Cool. Yeah, thanks so much for having me.
Yeah, of course. All right, later.